Can you guys see the screen?
Yes.
Okay, good.
Yep,
Thanks.
we can see it.
All right. Okay, so we should be all set, I think. And you can hear me okay? I got a new webcam, so I hope this thing works, but I guess you can hear me because you said you can see it. Anyway, let me know how this webcam works, if there's any problems with it. So let's see, I just wanted to go through the this I have the red pen here. Let me get a black pen. Hold on a second. All right. Sorry about that. Anyway. So I looked for papers this week and I found a bunch of them, but a lot of them were kind of rejected. But anyway, I put them all here, but I only used one for the homework. It's this Simon paper. So it's kind of simple. They have 3 polyelectrolytes. And then they have these vesicles that they make. So the vesicles are made, there's a cationic surfactant called CTAB that people use. So they use that surfactant and it's a dual surfactant system. So they have the CTAB they're using and tetradecyl dimethyl amine oxide, and they use the mixed surfactant system to make a more stable vesicle, I guess. And then they put into that vesicle, so that's going to be kind of plus groups, and I think it's like 13 carbons or 13 to 16 carbons. There's 2 surfactants they put in. So there's amine groups on the surface. And then within it, they put hexanol. So they end up with stable. So cationic surfactants make really stable structures. Anionic makes less stable. Anionic works better as a detergent. Cationic is kind of a softer detergent, I guess, so that they substitute sometimes cationic surfactants for anionic to make things better for your skin, I think, for consumer products. And then some of the anionics, like sodium dodecyl sulfate, which is like 12 carbons in a sulfate group. That's supposed to have some kind of problems. Like people are trying to remove sodium dodecyl sulfate from shampoos and things. Like if you go shop for shampoo, it'll say like SDS free shampoo. I don't know exactly why, but I think these are basically a little bit harsher. Soap is the harshest. Like if you just have a hydroxyl group on the end, that's the harshest kind of surfactant. And then the next harshest would be like anionic, and cationic is the least harsh, but cationic doesn't exactly wash as well. So if you want to make like a drug delivery, usually you use cationic because it's more stable. It's like a more stable. Other than that, there's whole books on surfactants, right? So anyway, so they're just using this, and then they have they have 3 kinds of polyelectrolytes they're using. So these look complicated. This one's simple. So this is acrylic acid and then stuck to a polymer, a vinyl polymer with acrylic acid sticking off the side. So that's like the simplest organic acid, carboxylic acid, and then polyacrylate, sodium acrylate. So that's a weak polyelectrolyte, and then these are also weak polyelectrolytes, right? So this is sodium hyaluronate, which is, so these look a lot like so that's the wiki page for that. But you notice that this backbone, this 5-member hetero ring, right, is the same as glucose. That's like the glucose ring. I mean, 6-member hetero ring, right? So basically that thing has a glucose unit in it, as does cellulose has the same thing, right? So does cellulose, has that same kind of ring with some hydroxyl sticking off, and then starch has the same ring in it, right? So there's a lot of biomolecules that'll have this 6-member hetero ring with oxygen, and then some hydroxyl thing sticking off. This hyaluronate is something that's in synovial fluid in joints, I guess, to protect bones somehow. So it became like a health food thing, like to help with connective tissue. So you'd eat it, and that somehow it would help you. So it became like something that was around. Anyway, so they're using that, and then that has a persistence length of let's see, I think it's like 9 angstrom per, or that one has a larger persistence length. No, it's 9 angstrom, and then the sodium acrylate has a persistence length of like 1.5 angstrom. Oops, that's not what I want. Sorry. Get the homework here, because I listed the persistence lengths in here. So you have sodium hyaluronate is 9 nanometers. It's a 90 angstrom. So you have like a 90 angstrom, so that's pretty large. And then you have 13 angstrom for this polyacrylic acid. And then this is sodium hyaluronate. Then they have carboxymethyl cellulose, which is like the cellulose, the same glucose chain, but it's got kind of a pendant charge group on the side that's less localized, and that's got 60 to 160 angstrom persistence length for the chain. So these are rigid, pretty rigid chains. This is a little bit more flexible, right? Depending on the charge, like those values will change because they're polyelectrolytes. Right. So the idea of this paper is just that you can make this, they used to call this a grapevine structure. So you have polyelectrolyte, these are anionic polyelectrolytes. So sodium's a counterion, it's positive, and then this carboxylic is negative. Then you have these cationic surfactants. You have this kind of setup, like you have your negative charges interacting with the positive charges, and then that'll stick these kind of nanospheres onto the chain, and then you can make ribbons with it, or make kind of linear structures. And depending on the persistence length of the chain, then so this is the structure of the beads that come out. This is a neutron scattering measurement. So it's log intensity, log Q. This is kind of log of the mass. So this is the mass versus 1 over the size. So if you have like mass goes with size to some dimension of the object. So if this is a linear object, that dimension's 1, mass goes with size. And this is inverse size. You expect this -1 if you have a rod. And that's what you get for the black one, which is the this hyaluronic acid, sodium hyaluronic acid, or sodium hyaluronate, right? Which has this long persistence length, which is 90 angstrom persistence length. So so you can see this is power 1 here. Then you can say, well, what's 2 pi over 90? So like 6.28 over 90. That'll give you the Q for where that power 1 should end, right? And that ends up being like 2/3, so 0.06, I guess. Right, so that should go, that's like 9.876. So it should end like there. And that's kind of where the power 1 ends. So that's good. So this is the persistence length is where that power 1 ends. It kind of ends there, I guess. And for the other one, it would be 13 angstrom. So it's like 6.28 over 13. So that's about like 0.5 or something, right? That's about half. So 2, 3, 4, 5. So that ends like right about there. So the red one, the power 1 part, kind of ends like right about there. So that this neutron scattering kind of agrees with the persistence length that they got from some other method. They got the persistence length from well, it's in the literature, and also they got it from light scattering in here. So they have this kind of messy system. It's complicated. So they're going to be named like the amount of methanol, 50 Me50 means 50 millimoles of hexanol put in the oil. So that's the oil. And there's a surfactant. And then this is the molecular weight of the hyaluronic sodium halurate, right? 150,000 grams per molar, 150 kilodalton. So, and then the 0.7 is this charge ratio. So the anions have negative charges, and then the surfactants have 1 plus charge for each surfactant molecule. So you can say, what's the fraction negative? So, and you want a matchup. You want that to be 50-50. So you'd say you make up this number Z, which is the number of anion groups on the polymer or in the whole system, divided by the number of anion plus the number of cationic groups. And that gives you some number. If it was equal, that number would be 0.5, be 50-50, right? But what they find out is that they don't get a miscible system. So you want miscible means on the bulk scale miscible. So here. This was the simplest paper that I found. So this, and I put a bunch of others up there that are more complicated, but I thought this should be probably a reasonable one. So anyway, so so when you have a paper, you can put in a supplemental information, and usually it's right up at the top. It says somewhere supporting information. So it means like stuff they didn't want to put in the paper because it was making it too long. So they have a bunch of numbers. It's too much to put in a paper. And then they have pictures of the thing. So you mix in 3 parts. You put in a surfactant. Actually, it's 4 parts because there's 2 surfactants. So they put in 2 surfactants to make stable spheres. Then they put in the hexanol, and they put in the polyelectrolyte, and it's all in water. So it's actually 1, 2, 3, 4, 5 parts system, right? So it's got quite a few things in it, and it self-assembles into these like necklaces of beads. So it's kind of interesting. The idea is that this would be like a way to deliver. I mean, usually people just say drug delivery. So you have an oil. Generally, a lot of drugs are oils. You can encapsulate it in this cationic polymer, then attach it to this string so that you collect some of these so that this could flow easily, say. And then it reaches some condition, like the salt changes or the temperature changes, and it will release this drug that's inside the vesicles. Right, so this is some kind of a drug delivery system, or it could be something else. Like they don't exactly say what this is going to be, but that's one weakness of this paper, is just like a kind of like look at to make these things, without that much purpose. So this is the Z number. So you have no polyelectrolyte. So you don't put any polymer in at all. It's just oil. It's just oil and surfactant, and that makes us clear macroscopically single phase. Right? On nanoscale, it's got spheres with oil in it. Then you add the anionic polymer to it, and the two things phase separate out. Like the polymer, the anionic polyelectrolyte phase separates out, makes two phases. Right? If you use, this is if he's using hyaluronic, this hyaluronic acid, right? So basically, in this case, when he has either carboxymethylcellulose or the hyaluronic acid, he gets a gel. Like this forms a gel. And if he uses the oh, these are two different molecular weights. So the hyaluronic 84 kilodaltons, and then this is hyaluronic acid with some other molecular weight at the bottom. Anyway, so when he gets above 0.7 for the C, so 70% anion and 30% cation groups, then he gets clear. And that's true for every system that he has. All right, so every time he gets to 0.7, it's single phase, that's these open squares. And then he gets this kind of biphasic, meaning cloudy, macroscopically biphasic region. And at the low end, we have no acrylic, no polyelectrolyte, then it's just soap and oil and water. So that's single phase. Right, so you have a region of two phase. He's interested in the single phase structure, like the clear square. So he wants above 0.7, and it's always above 0.7 here. So it's kind of interesting that that's always above 0.7. And why is it above 0.7 is kind of a question that isn't answered in the paper. So anyway, so that's kind of one thing in here. Then so he does viscosity measurement, and he does a really simple viscosity measurement, which could make you wonder. So he doesn't have a viscometer, he's got just a capillary. So he does Pucel's law. So he's going to do this capillary flow measurement with gravity, but I have gravity upside down here. So with this complicated system, you'd expect structure to change when you put it under flow. So this isn't exactly the best measurement to do, but nonetheless, that's what he does. So he measures just the viscosity of the system is proportional to the 1 over the amount of material that flows out, the mass of the Q, right? The flow that came out of the system, right? And it's got something to do with the temperature. So, but basically, he's going to just measure the flow and get the viscosity, and then the geometry factors for it, right? So if it flows more, he's got a lower viscosity. That's basically Pucel's law, right? And you can calculate it with the radius. It's like the 4th power of the radius of the capillary or something. But so it's just using a capillary viscometer. Since it's exponential, it's going to fall on Arrhenius temperature dependence, which is a strong dependence, right? So you have to be careful about the temperature in any viscometry measurement, especially solution viscometry. So he's got it in a thermostat bath, and he gets this viscosity of the system. And he does cryo-TEM on this. Okay, so the cryo-TEM is probably the easiest thing to understand. That's the last thing he shows. So he does a cryo-TEM, and then picture this, like block out the red things and look at it, and you see a bunch of dots. And you put in the red lines, and you can see, oh yeah, it lines up. So yeah, they're doing what he says they do. And then this is the acrylic acid one, where it's supposed to be, has a lower persistence. So it's supposed to kind of be joggy. And this is a hyaluronic HA, which is supposed to be straight lines. So you can see the problem with microscopy, you know. Whereas in this one, I can see a straight line right here. And in this one, I can see a jogging line right there. It depends which one I circled. And also this is TEM, right? And it's done by taking the solution, putting it into liquid ethane, and then putting it so it's at like 50 K or something, almost absolute zero, and then put that into a cold finger on a TEM under high vacuum that keeps it basically that temperature, so it doesn't, it's frozen in, right? And then you can imagine there's a lot of problems that could happen going through that process to get these micrographs. But nonetheless, he shows kinky things here and straight things there. So it's kind of successfully shows what's going on. On the other hand, neutron scattering, you take the actual thing at the temperature where you are, you don't need to freeze anything. You shoot a beam through it, and then you can get this scaling behavior. Right, so you can see a difference between the two. One is a straight rod all the way through, and the other one has this kind of kinkiness that it's got a higher dimension. So if you think like, if I have a Gaussian chain, then my dimension's 2, and I have a rod, my dimension's 1. Well, if I get 1.5, so the slope here is the negative of the dimension. If you get 1.5, well, that's kind of something between random walk and a rod. Right, so something, maybe a kinky rod. And so that's kind of what he shows. There's a couple problems with this. The length of his rods, so you can figure out how many spheres are in a rod using light scattering. And he does that here. This is how many spheres in a rod. And you can see this less than 10. So this picture is actually real, is like 6 spheres. That's not just an exaggeration. Those actually really are like 2 spheres, 3 spheres, 4 spheres, 5 spheres, 6 spheres like here. Right, so there really are just 6 spheres in this rod. So that's not exactly a rod. In other words, if you want to talk about scaling behavior, usually you're looking at having like 2 decades, not a part of a decade. You know, so so here you can see these lines. I didn't ask this, but this dashed line, so you can see if you can put your I can put the pin here, like you put a line to that, count how many decades. So if you go 1 decade up, 1 decade over, that's a line which will be parallel to this dashed line. So that means the number of spheres is proportional to the molecular weight of the polyelectrolyte, which is kind of what you'd expect for that cartoon of what's going on. If you have this cartoon of what the thing is, you'd expect if I make a longer polyelectrolyte, I'd have more spheres. So n spheres should be proportional to the length of the polyelectrolyte, right? So that's that dashed line in that plot here. So, but it's not the dashed line at all. In fact, it goes, if you count out the decades, you have 1 decade by 3 decades. So you do a diagonal across this to 1 decade, and you find out that's about the slope you have, which means that your number of spheres goes with the molecular polyelectrolyte cubed. Okay, so you have the number goes with the molecular weight to the 3. So that makes you wonder, like, what is going on? Because it should be, you predict n's proportional molecular weight to the 1 for a rod, right? Or for anything, if you have anything where it's gonna, even if it's not a rod, but if the spheres just add on to the chain like that, then it would be like how long the chain is how many spheres. But if you have a constant density of spheres attaching to chain, it would be n goes to 1. He has this goes to 3. So what could that be? I mean, if the rods were like this, so if the rods make a 3-dimensional object by clustering together, then this thing would fill a volume, and that volume would hold molecular weight to the 3 n thing. So you can construct something, you could possibly construct something that would follow that law, the law that's depicted here from the light scattering data, but it would be nothing like what he shows here, right? So it's kind of like a conflict. On the other hand, he's only got a half of a decade in size, and the sizes are less than 10. So there's only like 6, maybe this one only has 2 units, 2 spheres, right? So you can't really say there's a scaling law if you have 2 spheres, right? So some argument for and against whatever, and his prediction of the lines, you know, it's kind of questionable unless you get to some huge, you know, length, and you can't really talk about scaling laws in this. All right, so there's that business. So I thought this would be like a 1 question like I do a few papers, and this would be just like one question, but actually it went on, it seemed like I could fill out a whole quiz with just this one paper. To me, it's pretty simple, but it might be just about right. So you see he's doing figure S7, that's in the supplemental. So if you want to look at those figures, they're over in this supplemental thing, like the pictures. And this is what's dynamic light scattering. Okay, so we'll talk about this later on. That's the problem with these papers, is that they're comprehensive, so we haven't covered the material yet, so it's difficult. So, but in terms of this, this is a function you get out of the dynamic light scattering machine, and this is the time, basically. So you're plotting, this is an exponential decay, so you get a time at every knee in this curve, you get a time, and that's a relaxation time. That's the time for something to move around in the system. Right? So he's going to get a thing called lambda gamma out of that plot, and that's basically like time. Right. So, and then he's getting this, he measures this at different angles. Right. So it's a light scattering measure. So you shoot the beam in, you collect out at some angle. So that angle is associated with size from Bragg's law, like the d spacing is lambda by 2 sine of the angle. So that's called Bragg's law. That's what you use in diffraction. Right? See, so the angle gives you a size. So you have a size and you have time. So if you have diffusion, you said like that so the size is really a distance. In this case, you have things moving around. So it's a distance that they travel in that time. So basically, if you have distance and time, so you expect square root if it's Brownian motion or diffusion motion. The prefactor is the diffusion coefficient. Right, so you expect that distance goes with time to the 1/2. Right, so here, a lot of these he just has one time, and some of them he has 2 times. Right, the second time, so the long time of the slow motion he kind of ignores, or he talks about it, but he says, anyway, the first one is a diffusional motion with t to the 1/2. The other one has a weird behavior, which he shows in the paper somewhere here. Aggregates, the cylinders. What's that? It's a question. So let me just figure out what the question is. Wait to the 3. Dynamic. All right, so he just says this. He just says it in the text that as you change the angle, so it goes with distance squared, and the other one goes with distance cubed. So it'd be like, instead of diffusion, we have where did I write that? Distance. So you have distance goes with time to the 1/2. That's the signature of diffusion, or distance squared goes with time. He has distance cubed goes with time. So that means time to the 1/3. Right. And you remember we said, like, if the distance you travel goes with time to the 1, that's called ballistic motion. So that's go in a straight line in the field. This is 1/2 means you're going in a random motion. So you're going away from ballistic towards the direction of random, and then beyond, because you go to 1/3. So that's not exactly defined. Who knows what it is? But basically he talks about that here. So I mean, he says that's the answer he gets. So this cube root thing is something, he explains it in the paper, so you can look at what he says and see if you believe it or not. That's something kind of interesting that more or less has something to do with what we talked about. And then this is the power law stuff. So just do that Q calculation. And then he gives this equation for the end-to-end distance for a persistent chain, right? And he uses that. Let's see, this is on page 4064. So 4064. Here, so it's at the end of this. He gives that equation right here. right? And his reference 52, right, this was, I forget who derived this, but it was definitely not reference 52. He references a textbook, which is a pretty good textbook. I think I have it on the webpage, but basically he references a textbook for this equation, which is kind of like cheating, you know. I think this is equation from Kratky or Perot, one of those two. Either so one of the Austrian guys came up with this, Kratky or Perot came up with it. One of those two. But and then Flory, it's also in. You could have cited Flory's second book. Also like a Nobel laureate. Instead, he references 52, which is this Heitzman book on polymer chemistry, which is like a textbook. It's a good book, but it's not the thing you'd reference for that equation. Anyway, so he uses that to calculate the persistence length from his from something. I'm not sure why he mentions that here. Chains of n. Oh, because he does a simulation and he uses that to get the persistence length from a simulation. That's what that is. He gets the end-to-end distance. He knows the contour length. LC's the contour length. And again, like this equation, like if you get a large molecular weight, it just becomes the first term. So the second term drops out because e to the let's see, if you get a large, let's see, if LC equals LP, let's see, this has to go to 0. If LC gets large, that goes to 0. This is 1. Actually, this isn't the same equation that we had, but somehow this goes to just the second term drops out at large L. I'm not seeing how that works. I guess it's just because, all right, so you have LC, 2LC LP minus 2LP squared times 1 minus e to the minus LC over LP. And so at large, when this goes large, this term goes to 0. So you just have 1. Then you have 2 LC LP minus 2 LP LP. And LC's, if it's larger than LP. So that term drops out and you just have this term. Right. And then to get the Kuhn thing, and this is for R squared, and you know that thing equals LK squared times NK, which equals LK LC. So then 2LP has to equal LK. Right. So anyway, so that does the same thing as the equation in class, but this is a different equation. It's a little bit different. The Heimitz book, I think we have here. So he actually doesn't say where it is in the Heimitz book. Not found. Anyway, I do mention Heimitz here somewhere. Because I spelled it wrong. Oh, this is a book. This is a Heimitz has 2 books. One's on colloids and the other one's on polymers. There's 5 matches though. Heimitz 84, 97. See if I can find it where he has that equation in here. So that book is here. If you want to look at it in more depth. Let's cook and I'll come over here. That's about it for this thing. So the spheres, if you just had spheres, you see this is a neutron scattering data log plot, but if you just had spheres, this thing would be flat and then it would have this kind of oscillation. And this cutoff, this peak here is kind of the radius. So it's like 2 pi. So there's a peak here also. It's like 2 pi over that peak is basically the radius of the sphere. And this would be 4 pi over that q star. The second one would be the radius of the sphere. Or let's see, half of that, like pi over it. So it'd be like q star, 2q star, they're orders. And that basically you can get the radius of the sphere from where the peaks are in that. The reason it has peaks is because the sphere is a perfect object, so it has a cutoff point, and you have a diffraction between those 2 points that leads to the peaks in it. Right. So anyway, that's spheres, and this is the scaling, means that it's in a chain, that it has a power scaling instead of flat. So that's how you'd read this, like going from small to large. You go and you see the spheres, they have a diameter, and then you see larger size and you see that it's a chain. So you get this scaling for the fractal chain structure. And then that ends here where that goes flat. So you have the chain structure and then it ends, that'd be the overall size of that chain would be like 2 pi over this q. Right. So anyway, so those things, we'll talk about that more later on, I guess, but anyways, that's it for this paper. Any questions on this thing? On that paper? That's what the quiz, the homework's about. It's just that paper, a few things. Again, all the papers like go into things we're going to talk about later on, but they dump it in now in order to talk about persistence. You know, in polyelectrolytes, you kind of need to include some of the things from later. So that's just how it is. And I had quite a few papers here to look at. And I tossed out all of them except that one. So that's one that seemed to be the simplest. One is almost the same thing, but more industrial. So they're using, when you have a water treatment, it's like the Cincinnati Waterworks down the river. So sometimes we tour that with the undergrads, but they basically have they take the water from the river and they put it into ponds on a golf course, believe it or not. Then they go from the golf course into flocculation tanks, which are giant tanks with these paddles that spin around. And into that, they put a polyelectrolyte. Right, so they put this something like they probably don't use polyacrylamide because that's a carcinogen, but basically, at least the monomers are carcinogens. So they don't usually use that, but basically this is looking at that kind of thing, like flocking out cationic, or flocking out, let's see, acrylamide is an anionic polyelectrolyte, so they're flocking out cationic particles, and the thing they're using for that is bentonite, it's like clay, so it's sheets. So it's platelets that are negatively charged on the surface. Then they put in this acrylamide that's positively charged, and it does exactly what they were doing with those spheres. It's going to make like a grapevine structure of bentonite nanoparticles stuck to this flocculant. And if you get enough of this, this thing will like gel up, and like you can separate the dirt from the water. Right. So that kind of process is used here. He mentions where it's used: paper manufacturing. So Josh knows, and enhanced oil recovery. I don't know, somehow you put it into a fracking well, drag reduction, drinking water treatment. Right. So that kind of thing where they're doing the spheres, this is a real application of it, more or less, even though it's in soft matter, which is kind of a sciencey journal. And they put it in a Taylor-Couette viscometer. So it's a different kind of, it's not a cone and plate viscometer. So this is a cup and bob viscometer. So you have and then if you're doing this industrial scale, sometimes they get rid of the cup and they just have a bob. So you just stick a bob into a bucket. And this is like a paint company, and they just spin the bob and you get the torque, and you can get the viscosity from the you can also do this with an oscillatory viscometry or continuous. Right here they're just doing continuous. Spin the bob in the cup, and then you get the viscosity. Again, it's not a constant gamma dot across the gap, because you have a velocity at the surface, and then the fluid's going to basically make a parabolic profile across the gap for the velocity, and then there's different shear rates. The slope of that velocity profile is the shear rate is not constant in a cup and bob viscometer. The nice thing is, if you want to do light scattering through this, you can put a quartz window, you can get a quartz bob, and shoot the beam right through it and get like dynamic light scattering, static light scattering. So we can get this gamma thing, the time dependence for the fusion. You can get the structure, like how many flux cluster onto a polyelectrolyte. And if you have a big one, you can put a 1 centimeter beam of neutrons through it and look at the structure, or you can shoot an X-ray beam through it if you want to use beryllium windows in it. So this cup and bob viscometer is popular for optical measurements, even though it's not ideal for the geometry for flow. So you can shoot a beam right through it, right? So anyway, so that's not what they're doing, but that's kind of a little bit. So we have, so far we have 3 kinds of viscometers, like a Purcell flow capillary viscometer, this cup and bob Couette viscometer, and the cone and plate viscometer. And there's also just a variant on cone and plate is plate and plate viscometer, right? So these are the kind of viscometers people use for polymers. Generally, like plate and plate is the easiest because they treat it as if it's a cone and plate. And then you can, with this, if you're dealing with something that's really viscous, you don't get as much melt breakdown, or you can have actually fracture of the melt in the viscometer, right, for polymers. So maybe we'll talk about that later. Anyway, so they're doing the same thing. It's not on the quiz, but basically, I thought it was kind of interesting. They find out that when they add this flocculant, they're trying to pull out the, they come up with an optimum polyelectrolyte concentration. It's actually kind of an interesting paper. They did some optical pictures of what's going on. It's under shear too. So the flocculation here, that's why in the tank for the water treatment, they have giant paddle flowing. So you need to mix up the bentonite with the polyelectrolyte. So they have to have like a collision with it somehow. So you have the anionic and the cationic, they have to kind of collide in order to flock, in order to bond with each other. So you need the stirring. So this is a kinetic study of that kind of thing going on. Like versus time, how the flocks grow. You know, so I thought it was kind of interesting. So it's polyelectrolyte. The problem is it doesn't have much about persistence like that, right? Even though it's a polyelectrolyte. Right? So that was rejected. Then there's a paper on simulation. There's a lot of papers. This is simulating a polyelectrolyte. You can see the counter ions in polyelectrolyte, and then it's under an oscillating AC field. Right. So this is like last year. And then this is used for the reason that's of interest. Oh, that's the Heimitz book. I wonder if I can find. No, I can't do it. Do a search. Anyway, the Heimitz book is here if you want to search for the persistence line. It talks about it in there. What did I want to? Oh, all right. So this is so this thing about the polyelectrolyte folding comes back to collapse a chain, then comes back to this. So they have, this is a Nature paper. So they have what they call MEMS, micro engineered machines, right? Which a lot of times are little micron, like 10 micron capillaries, and then you put blood into it or some other kind of biofluid. Then you can have like some testing. So this would be like a diabetes blood sugar tester. So capillary forces pull the fluid in. You have various ways to split it up and mix it. So you're going to make a machine. So actually UC is the center for this kind of technology. Chang'an is like one of the leaders in that. He's in the electrical engineering, and there's some people in the chemistry department that do this also. So anyway, so this is ideal. Like if you want to check for genetic markers like DNA, you put the DNA into a gel and you put an electric field on it, right? And the DNA will like travel across the electric field. How far it travels, depending on what the gel is, tells you what the genetic makeup of the DNA is. It's called gel electrophoresis. Right. So the idea is like put gel electrophoresis into one of these MEMS devices. You can take a drop of blood and tell if somebody has a cancer marker or something, some kind of genetic marker. Because right now that would take like, you'd have to take a huge amount of blood, ship it off to San Diego. They do some kind of testing to see if you have this cancer marker to tell what kind of cancer you get. And with this kind of MEMS device, you could do that. A nurse could do it in a doctor's office. And you could screen a lot more people for a lot less money, right? So it's because this is just going to be one drop of blood and a really small amount of reactants in it, right? So anyway, so it's this, and then when they do that, so anyway, with DNA, it's been found that you can put the DNA in, and if you put it to an oscillating electric field, it folds, and the folding depends on the sequences of the DNA. So there's some interest in this idea, like DNA folding in an AC field due to that kind of device. Again, this is like a Nature scientific report from 2018, I guess. Looks like it took them a while to publish it. It took 2 years for them to accept it. It's a tedious path. Anyway, so he's doing that simulation, and it's got to do with persistence. So you can see like the overall coil size and going on with this electric field. So he increases the electric field until it folds, and this drops down as a universal behavior in it. And he's got pictures of it. It's got something to do with the persistence length. I thought it was kind of an interesting, so depending on what the capillary size is, that's an RP's capillary size, you have to have a certain range for this folding phenomenon to happen. It's also got to do with the electric field. It's kind of an interesting paper, but basically it's dealing with things that are too far from what we're doing. I thought it was kind of interesting, but so I stuck it there so you can look at it if you want. And then there's a paper that's too much for us. It's just on rheology of polyelectrolytes. This guy Lopez from Aachen, Germany. And he goes through pretty extensively like polyelectrolyte rheology. That's also from this year, I think. It's in the Journal of Rheology, 2020. Right? So it's kind of too much, but I put it in there. And then what do we have? A few minutes. 2 PEs, and then there's, all right, so the double helix. So there's a Nature paper on double helix that looked pretty good for the homework. I didn't do that one either because it's really just about X-ray diffraction of a double helix. So it's a polyelectrolyte. So, and it's a polyelectrolyte, right? And it forms a double helix, like just like DNA. So it's interesting. And the diffraction patterns are just like the Nobel Prize, Watson and Crick's Nobel Prize lecture was all diffraction patterns just like this. It's kind of interesting in that sense. The story is there's a woman that actually discovered it and they ignored her, right? But this guy cites the woman here, Rosalind Franklin. So he says like Watson and Crick won Nobel Prize, she didn't. So it's like, but she was and worked with them equally, right? Something, I think that's the story. But anyway, so I thought that was kind of interesting too, but it doesn't really deal with persistence. It really has to do with the double helix, which is related to persistence, but seemed too far. Then there's a lot of papers, that I found, but anyway, they're all here. I threw them in there. This is about conjugated polymers and persistence length in conjugated polymers. This one probably would have been a good one to do, but I chose the other one. I think just because I looked at it first and I realized there was enough in it. Conjugated means, it's double bond, single bond, double bond, and that can conduct current if you dope it. Okay, so you can dope it because these can switch. Double bond can go here and there. It's a resonance structure, right? So basically showing the double bond here isn't true. It's actually in all the bonds, right? So the whole thing is free electrons. And they have large persistence because this structure, this bond is planar, right? So this bond is the tripod thing. And it can spin, and this is planar. So if you have double bond, then another double bond, and that entire structure is all in a sheath, like it's all planar, means it's rigid. Right, so you're gonna have a huge persistence when you have these. That's why they don't dissolve, because there's no, like delta S for mixing is 0, because it doesn't have any conformational entropy. It's just one state, right? So these are hard to process. Like, that's the problem with conjugated polymers, is you can't process them. You can't extrude it. You can't do anything. So how you made it is what you got for those usually. Anyway, unless you can put functional groups on them that can make them have specific interactions that will dissolve in some kind of solvent. Anyway, this goes on and on. They measure the persistence length. They predict it. They do some simulations. Side chain length versus persistence length. This is similar to the simulations and the other thing, those other papers. But anyway, that's a pretty good paper to look at. I think it's in Macromolecules. So that's another one. This is about batteries. I was trying to find something about batteries, but this is about a different kind of battery. We use polyelectrolytes as an ion conductor, and it talks about different groupings of the ions. You can have free ion in the solvent separated, or you can have like a contact ion pair, and then the fractions of those as you change the lithium ion content in a solution, right? And then how that affects the conductivity of it for a battery. So you can see, like, as they change the lithium concentration, the persistence length drops. This is a screening effect. In other words, you have a polyelectrolyte. As you add more counter ion, you screen out the charge. Then you have less charge interaction. You have a lower persistence. So this is a pretty good paper too. But anyway, I picked the other one. This one might even be better, but anyway, I didn't use it. So that's about it. There's a lot of papers on the subject. None of them are exactly right, so this first one's kind of interesting because you get a understanding of like how the persistence length, how you can build self-assembled structures, and take advantage of these ideas like persistence, charge interaction, screening, to talk about how to build like nano machines, I guess is what we're talking about, from molecules. So, but there are a lot of different areas, like, so just dump those papers there if you want to glance at them. You can look at them. So any questions, anything? That's about it for today, I think. So see you guys on Monday for normal meeting.
Have a good weekend.
Yeah, have a good weekend, you guys. Try to stay warm.